So for question 5, here we are given a function hx, and it's an exponential function because it's a to the power of x. Okay. They also give us a point on the function here. The x coordinate is -1 and the y coordinate is 1/2. We can use that point to actually determine the value of a, which is the second question over here. So let me do that question first. I'm going to calculate the value of a by subbing in those coordinates. Okay. Now, x is -1, y is 1/2. Then a to the power of -1 can be written as 1 over a, right? And we can cross multiply to get a equal to 2, right? You're basically just multiplying a with 1 and 2 with 1, and that gives you 1a equal to 2. Okay, so let me just fold that in. Instead of having the a there, I can now just substitute our actual value, which is 2. So we have 2 to the power of x. Okay. Now, my first question is actually write down the coordinates of q. And they kind of didn't point out where q is. They just placed it near this y-axis. So I'm assuming, because there's no specified statement here, but I'm assuming that q is the y-intercept of the graph. And to calculate a y-intercept, you'd have to make x 0. So I'll say 2 to the power of 0. I'm basically just replacing this x with 0. Okay, so 2 to the power of 0 is equal to 1, and therefore the coordinates of q is 0 and 1. We substituted x with 0, and we calculated the y as 1. Let's on to the next question. Now, we know the equation of hx is 2 to the power of x. They are now asking us to find the inverse to this h function. So you start off by swapping x and y. And then you solve y using a logarithm. Okay, your base is 2, the argument is x. So you just put that in place. Okay, sorted. Now it's time to sketch these functions. And I'm going to sketch the log function on top of, well, not on top of, but like on the same set of axes as this exponential function. Now, to sketch the inverse graph, you just need to use the same points as the original graph. So remember, the original function had point P with the coordinates -1 and 1/2. Now you just swap those points around. The x is now going to be +1/2, and the y coordinate will be -1. So +1/2, you find that on your x-axis, and -1, which would be somewhere below, you find that on your y-axis, and then you plot the point where those two values meet each other. So I'm just guessing it's going to be somewhere here. Let's call that P prime, 1/2 and -1. And you also want to plot the y-intercept. Oh, actually, so this y-intercept, point Q, which had the coordinates 0 and 1, that is now going to become an x-intercept because we swapped x and y around. So the coordinates is actually going to be 1 and 0. So it will be somewhere here. Okay, and this graph is going to take the shape of, you can see these things are not drawn to scale here. The original graph is not drawn to scale, but it's going to take the shape like that. Okay, this would be the inverse of h. The graphs will look a lot better if they were actually drawn to scale, but unfortunately the one that they gave us is not drawn to scale. Okay, the line of symmetry for these two functions is a line that goes directly in between them, having the equation y equal to x. You always want to put that line of symmetry there whenever you draw an inverse function next to the original function. Okay. So there we have the 2 points, right? It's very important that you also have your intercept with the x-axis, and you can put the coordinates in that 1 and 0. That would be q prime, by the way, not just q, but q prime. And then question 5.5. So remember our inverse graph looks something like this. Question 5.5 is asking us, what is the domain of this function? Okay. Now, as we look at this graph, you want to check at what x values does the graph pass through? What are all the x values that the graph passes through? Now, this graph, it looks like it goes through all the x values as we go from 0 to infinity, but it doesn't ever pass 0. Like, if you look from right to left, it never goes past the y-axis. Okay, there's almost like a limit, an asymptote, in other words. So the domain of this function is only the x values greater than 0. Not equal to 0 because there's an asymptote, but only greater than 0. All the x values to the right. Okay. Our very last question over here, it says, hence or otherwise, determine the values of x for which log of 2x is greater than 1. Okay, so they're talking about this log function that we drew, and they're asking us, where is this log function greater than 1? Okay, so first I want to find out where the log function will be equal to 1. Okay, so let's solve that. Log 2x equal to 1. Okay, we're going to reverse the log by taking the base, raising it to the power of the exponent, and that's going to be equal to our argument, which is x. So, in other words, x is equal to 2 to the power of 1, which is just 2. That means that this x value for that point is 2, and the y value is 1. Okay. Where is the function greater than 1, right? Where is log of 2x greater than 1? Well, it's all the x values greater than 2. For all these values where x is greater than 2, let me erase this. For all these x values greater than 2, you'll notice that the function is greater than 1. Okay, because that's where the function is equal to 1. And if you substitute x values greater than 2, then the function also goes greater than 1. All right, and that's it.